problem I'm going to talk about today is the greatest common divisor. We all know that the reduced form of 8/12 is 2/3. But when we are talking about larger number like 255/7068 or 17,572 over 15,756,712, the trivial solution for this problem is checking all the integers from 1 to the minimum of those two integers and check if both numbers divided by this I, with no remainder. We can see that the efficiency of this solution is a big O of n, where n is the minimum of a and b. This solution may work for smaller number, but it will take a long time for larger number. A better way for finding the GCD of two integers is the Euclidean algorithm. This algorithm is based on the concept that the GCD of a and b is also the GCD of the remainder when we divide a by b. The proof for that is the following. By definition, we know that a equals to x times the GCD of a and b for integer x, and similarly b equal to y times the GCD of a and b for integer y. From our definition for r before, we can say that a equal k times b plus r. Therefore, r equal to x minus k times y times the GCD of a and b, means that r is also divisible by the GCD of a and b. Let a be the larger number, and each iteration we will set a to the previous b, and we will set b to the previous remainder. If we will repeat on this procedure until the remainder is 0, the greatest common divisor of a and b is the remainder of the one before the last iteration. Here, I will show the recursive way of the algorithm. I will start each call with calculate the remainder r. The base case is where r equal to 0 and we will return the previous r, which is now b. If r is not 0, it will call the function again with b as the new a and r as the new b. The algorithm performs better than big O of log n because usually each iteration the numbers get smaller by more than half. The algorithm never requires more steps than 5 times the number of digits of the smaller integer. Therefore, the big O of this algorithm is big O of d, where d is the number of digits of the smaller number b. The greatness of the Euclidean algorithm is not just by finding the greatest common divisor, but also it's leading to the extended Euclidean algorithm. Let C be the GCD of A and B. So from our proof before, we can say that C equal to x times A plus y times B. It is also known as the dopamine equation, an equation with only integer solution. The extended Euclidean algorithm gives us its specific solution. We should define between 3 different cases. Case 1, where C is the GCD of A and B, like we saw before. Case 2, where the left-hand side is a multiplication of the GCD of A and B. In this case, we will just multiply the equation by the integer k. Case 3, where the left-hand side is not a multiplication of the GCD of A and B. In this case, there is no integer solution for the Diophantine equation. Therefore, the Euclidean algorithm is a way to know if there is a solution for the Diophantine equation. Let's see how does it work. On the left, we can see the process of finding the GCD of 33 and 12, which is 3. If we will take equation 2, we will be able to define 3 in terms of 12 and 9. We can do the same with equation 3 to define 9 in terms of 33 and 12. Let's plug equation 3 in equation 2. At this point, 3, our C, defined as a linear combination of 33 and 12, which are A and B accordingly. We can see that the specific solution is -1 and 3. We can see from the graph that the solution we found before is just one of infinite solutions. In order to find all the solutions, we will use the following equation, using k as any integer. The Diophantine equations are main subject in solving chemical equations, cryptocurrency methods, and many more areas. Thank you for watching my video. Until the next time.